Okay, so I'm sorry my lighting is getting bad here. It's getting a little bit late and it's a little cloudy outside, but the problem for now is looking at homework problem number 17.9. Alright, so let's see. 17.9. I think I might be a little off camera here. Okay. All right. So the question is for 17 point, and basically derive delta E delta T is greater than or equal to h bar over 2. What's the significance of this? Well, recall please that delta X delta P is greater than or equal to h bar over 2. What's the name of this? Really famous. Really famous. A lot of people, even who don't know physics or chemistry, have heard of that. It's a principle. It's a principle. Yeah, it's an important principle. Please name that. Okay, so the first part of this, deriving this equation, which looks just like that, right? The first part of that is, given this, that E is P squared over 2m, the energy is P squared over 2m, and that dEdt is simply the change in E over the change in P, we're supposed to show that. Okay? Alright, no big deal. So we know that E is a function of P, which is P squared over 2m. This is a definition, maybe, or it's maybe something that we memorized at some point. We derived it once or twice in class by looking at E is equal to 1/2 mv squared. Alright, so that's essentially the kinetic energy. Okay? Now, if dE dP then is going to be 2P over 2M, right? By looking at that. Agreed? See that? Just bring the 2 down? Alright. And this is the same thing as the change in energy over the change in momentum. Now, we know that momentum is mv, and this is over 2m, which is equal to change in energy over the change in momentum. Okay? So it looks like V. Yeah, these two cross off, right? Boom. V is equal to the change in energy over the change in momentum. So if we isolate for the change in energy, then we simply get V, that's the velocity, d momentum. Okay? And that's what I was supposed to find out for part A. So QED. We showed it. That's what QED means. Alright, that's part A. Okay, part B is given V is equal to dx dt, which that's what we learned. You know, that was from our Algebra 1 class, I think, where we said, you know, a train in Chicago heads to New York. The distance between them, that's the change in x. It takes, 12 hours. That's the change in t, right? What's the rate, velocity? So this we've been looking at for a long time. So we know that velocity is equal to delta x over delta p. So therefore, delta E is equal to delta x over delta t, delta p. Okay, so delta E, delta t is equal to delta x, delta p. And we know that this is greater than or equal to h bar over 2, which is the Heisenberg uncertainty principle. Okay, so we've shown that B also, that's part B, we've shown that this is another implication of the Heisenberg uncertainty principle. All right, the final question that we have is, what's the spectral line width? All right, what do you mean by that? Wow, what's the spectral line width? All right, remember in IR spectroscopy, we had stuff that looked like that, right? Well, we know that if that this came about by hitting bonds. This was vibrational, right? By hitting a bond that had one particular characteristic energy with a photon, and then when it let that photon back off, it will go back to E2, right? So it's going from one energy state to another. How long does it take to go? That's the lifetime. That's what lifetime is, okay? So if the lifetime of a particular energy transition is 1 times 10 to the negative 9, then that's what that line width is. All right, but you might be seeing yourself, if this is just going to emit a photon, and those photons are all of a particular wavelength, why is this not really sharp? You'd think that IR spectroscopy would be like bink, 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 right? Bink, bink. Why do they have any line width at all? Line width. And I'm only telling you this because oftentimes it's the jargon that's scary. So what is meant by spectral line width? We're talking about this kind of thing right here. Okay? So that's, and this is also measured in reciprocal centimeters, which is an energy. So it turns out that the particular bonds will have an energy, will have a lifetime of certain times, which we're given here in the question stem, right? And that lifetime, the greater the lifetime, the greater the line width, or rather, the less the line width. Wait, I got to think about that. Forget it. Forget that I said that. We'll think about it and come back and say it in a different video. But either way, we know now that the lifetime times the line width, right, it's got to be greater than or equal to h bar over 2. Okay? So the question is, if you have a lifetime of such and such, what's the spectral line width? And that's sort of how we interpret that. All right, so let's derive this. dE dt. Now we know that dE is equal to hd nu, right? Yeah, okay. So we're asked for the line width. I remember now. In the question stem it says give it to us in reciprocal seconds or reciprocal centimeters. First of all, we'll do reciprocal seconds. And so if we're doing it in reciprocal seconds, it'd be good to have frequency, which is reciprocal seconds. Okay? So if we know that dt, that must also be dt, or delta t. Agreed? In this is equal to that, which is greater than or equal to h bar over 2. Okay? So let's say delta nu is greater than or equal to, or h delta nu is greater than or equal to h bar over 2 delta t. Okay, now we're getting somewhere because I'm looking for an energy in terms of reciprocal seconds, which is going to be that. So I just isolated that. Now look, I can cancel out the h's because this is greater than or equal to h over 2 pi. That's my h bar times 2 delta t. Right? I can cross those off. So it looks like, let me come over this way. I'm running out of space over here. Delta nu is equal to what? 1 over 4 pi delta t. Okay, so I can now calculate. Now I can take my lifetimes, plug them into this, and I'm done. Let's do that for one of them, and then we won't do it for the other one. 4 enter pi times 1 times 10 to the negative 9 times, okay, and then we take the reciprocal of that, and that goes to be 7.96 times 10 to the negative, or rather times 10 to the 7 reciprocal seconds, okay, and that is the line width. Okay, now I won't do that in reciprocal seconds. I'll let you guys convert that reciprocal centimeters. I mean, I'll let you guys convert that yourself. But remember that nu is nu is equal to 1 over that. Remember that. You're going to need that in order to calculate that in order to convert that to reciprocal centimeters. So I'm going to let you guys do that on your own. Okay, hope that's helpful. A lot of information.